How are y'all doing? So my name is Sharon Glotzer. I'm a professor at the University of Michigan. I teach chemical engineering and material science, but I'm actually a card-carrying physicist. I got my bachelor's degree in physics at University of California at Los Angeles, where I grew up in LA, California. And then I got my PhD at Boston University in physics, studying statistical mechanics and critical phenomena, and spent 8 years at a national lab called the National Institute of Standards and Technology in Gaithersburg, Maryland, which is a fundamental science lab that kind of works with industry. And then I moved to the University of Michigan. So I have a pretty large group, about 30 PhD students, postdocs, and research scientists, where we study soft matter and self-assembly and anything that involves the emergence of patterns. I'm obsessed with patterns. And so that's how I got into studying quasicrystals. All right, so I'm going to talk about soft matter quasicrystals. So if you're someone who's traditionally in the soft matter community, you don't usually hear about or talk about quasicrystals. And if you are in the quasicrystal, the diehard quasicrystal community, chances are you're a metallurgist and you don't even think about soft matter. It's like completely irrelevant to your world. And so the juxtaposition of the two is something that I think is really interesting, and is something that's really only come about in the last decade or so. Let me just first mention that I'm going to show also some results from our group, and these students, Pablo Damasceno, Michael Engel, Amir Haji Akbari, Chris Yakovell, Aaron Keyes, and Carolyn Phillips contributed to doing all of the work that I'm going to show you, and I'll indicate who's done what. So this picture here in the background was something we were hoping to get on the cover of Nature Materials, but failed in January. You never know what they're going to pick for a cover. Once I lost out a really awesome picture of a twisted nanoribbon to a tiny, whiny, preemie bird that was just like this. That was more interesting. Anyway, so Michael Engel, Pablo Damasceno, Carolyn Phillips, and I have a paper that I'm going to talk about at the end, because it's illustrative of sort of where we are right now in understanding quasicrystals and what we can learn from them. So let's start by talking about what quasicrystals are. So back in 1981, 1982, Dan Sheckman, well, I realize that I have no pointer or anything, but that's okay. So Dan Sheckman and his colleagues at NIST, but mostly Danny, were doing experiments. These are all metallurgists, and they were doing experiments on aluminum manganese, and looking at metallic solids, looking for crystals. And he found something that he couldn't understand, didn't make sense, spent a couple years trying to understand it. John Kahn, who's a very famous material scientist who's retired now, helped him to figure out sort of what was going on. And he was studying this metallic solid and found that it had long-range orientational order, but something that was inconsistent with lattice translations. So what does that mean? It means that if you have a crystal, regardless of how complex your crystal is, the atoms are arranged in a periodic array. You can find some unit cell, some repeat unit, that if you translate it around, you can reproduce the entire crystal. In this structure, there was no such thing. You could not find the repeat unit. But instead, you could see that there was something ordered about it, and we'll go through and see what was ordered about it. And so this paper was published in Phys Rev, and I should say that all this work was done. Then it was called the National Bureau of Standards, but when I was there, much later, it was called the National Institute of Standards and Technology. And I worked with John Kahn. I didn't work with Danny Sheckman, but there's a lot of history in the hallways. And so what's really interesting about this discovery is that, unlike most discoveries in science, it can really be pinpointed to an exact date and time. I also realized that I have no clicker. So I'm trying to think of how I can most easily get to this thing. So so there's a notebook that shows his, when he found this. So it was April 8th, 1982, a Thursday morning in the electron microscopy lab. He was Dan Sheckman is an expert in electron microscopy, and he was on sabbatical at the National Bureau of Standards to do some experiments. And so he looked at this rapidly solidified metal alloy of aluminum and manganese, something that should form some kind of complex crystal alloy. And they were interested in ultra-strong alloys for aerospace application, which is sort of interesting because 14% manganese, which is what they were working for, is actually brittle, which is unusual for an aerospace application. So they were studying this, and he found this thing. And so this is a picture of his notebook. I have like, I don't know, a dozen of these green notebooks in my basement, but they don't contain anything anywhere near as interesting as this from that time. So he had a scattering pattern, and it looked like this. And so when you see Dan Sheckman give a talk on this stuff, the way he says it is, he looked at the scattering pattern and he started counting dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can't be. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can't be. So he started counting these dots around and said, but this is inconsistent with crystallography. This is not something that's allowed crystallographically. But clearly you look at this and you see sharp diffraction peaks, right? It's not diffuse. There is clearly scattering going on. And there's definitely some order to this pattern. So, and so there he is indexing this. And you can see up here, he says, he writes tenfold, question mark, question mark, question mark. So again, the reason why this is interesting is because until that point, anybody who was doing any crystallography was studying crystals, like sodium chloride would be a very simple example of a crystal, where you would have a diffraction pattern that looks like this, where you can index all of the peaks and everything reconciles and makes sense from a crystallographic point of view. But what they found was something really different. I'm just going to keep moving this out of my way. So they found something that has icosahedral order to it. And so they grew a crystal, and if you imagine that there are atoms at each of these vertices, and it makes up this big icosahedron. And this is a 5-fold direction. There's a 2-fold direction and a 3-fold direction. So here it is. So 6 5-fold, 10 3-fold, and 15 2-fold axes. That's characteristic of icosahedral symmetry. And this was the first time that anything like this had been, at least maybe not seen, but at least noticed and questioned, and they tried to figure this out. And so there was a lot of excitement at that time, then trying to figure this out, writing up this paper. At the same time, so that paper was published in 1984. And at the time, Linus Pauling, who's one of the most famous chemists ever, was very discouraging of the work. And he gave the whole team a very, very hard time. There's a famous quote from him at the American equivalent of the meeting that we're at now, the APS meeting, which is held every March. And in 1987, that's the year that I started grad school, there's a quote at that meeting. He said, Dan Sheckman is talking nonsense. There are no quasicrystals, only quasi-scientists. So that's a bummer when Linus Pauling says that about your work. And so he had he gave some explanations of what was going on. But at the same time, in the physics community, okay, so the chemistry community, the crystallography community, they were like, this is complete nonsense. This is completely the wrong interpretation. We're not buying it. But at the same time, there was important theoretical work that was going on completely in parallel with that. So earlier, even in Alan McKay published a paper called Crystallography in the Penrose Pattern, where he sort of discovered this kind of a pattern theoretically, and said that it has local 5-fold axis and represents a structure outside the formalism of classical crystallography and might be designated a quasi-lattice. So this work wasn't wasn't known to the NIST team. It was published, I don't know, it was published in Physica, but there was already the laying of the foundation for, theoretical foundation for these interesting kinds of patterns. And Dov Levine, who was at the time a graduate student with Paul Steinhardt, who's now at Princeton, then they were at Penn, and Dov Levine is at the Technion in Israel now. Dov Levine, for his PhD thesis, had the idea, knew about McKay's work, and said, you know, what if you could actually have, not just in 2D patterns like McKay was talking about, but in 3 dimensions, if you could have this kind of structure where you had no long-range translational order, no repeat unit, but long-range orientational order. And they called it quasicrystals. And when Paul Steinhardt tells the story, he says that he was teasing Dov about it and said, they got the name because because Paul said, what a quasicrystal that would be. So they still call it quasicrystals. The rest of us call it quasicrystals because quasicrystal sounds weird. Okay, so that's where that's where they got this name from, okay? And so you could say here, a quasicrystal is a natural extension of the notion of a crystal to structures with quasiperiodic rather than periodic translational order. Here they're classified by their symmetry under rotation. It showed that many disallowed crystal symmetries are allowed quasicrystal symmetries. They for the first time, they analytically computed what the diffraction pattern of an ideal quasicrystal might be, and they compare it. They say that we show that the recently observed electron diffraction pattern of an aluminum manganese alloy, and they're referring to the NIST work, is closely related to that of an icosahedral quasicrystal. And so the physics community was much more receptive, I would say, to than my understanding. I was a graduate student back then, or actually a high school student back then. No, yeah. Anyway, okay, so why were quasicrystals not discovered before 1982? They're actually not rare. You see them a lot in the laboratory. They had been thought for a long time that maybe they weren't stable, but they are stable, very stable. And they're actually really pretty straightforward to make. And this is a crystal, this is 10 millimeters here, this scale bar, of an aluminum, palladium, manganese, icosahedral quasicrystal from Bice in Jülich. Just to show you how you can actually get a really robust chunk of quasicrystal. And we're going to go into the details of what is a quasicrystal, how do you get it, how do you characterize it in a minute. But I'll mention that since the 1984 publications, there have been over 10,000 papers on quasicrystals. It's seen, I mean, so in material science, first of all, it changed crystallography. So the international, whatever it's called, Committee on Crystallography had to change the definition of a crystal because of the recognition that you could have these funny kind of quasi-periodic crystals. They have interesting properties in terms of friction hardness and heat conductivity. It gave rise to new synthesis methods. In physics, there's some interesting things about stabilization of quasicrystals that we'll talk about, entropy versus energy. We'll talk about their possible electronic properties and photonic properties. And they appear in soft matter, which is what we're going to focus on. In mathematics, there's all this diffraction theory and tiling topology work that grew because of quasicrystals. In geology, there's a natural, so there's another great story that Paul Steinhardt tells that really they should make it into a movie and they should cast Harrison Ford as Paul Steinhardt, which is that there's this great story, they found a tiny little piece in a museum in Florence that they thought that was an icosahedral quasicrystal that they tracked to the Kamchatka Mountains in Russia somewhere, that they thought was a naturally occurring, the first and only naturally occurring, naturally found quasicrystal, meaning not made in the lab. But it turns out that it came from a meteor, icosahedrite. So they're still on the search for a naturally occurring quasicrystal. But if you go back to 11th and 14th century tilings, you see these things everywhere. So this is an image from a shrine in Iran from 1453 CE. that shows these kinds of quasiperiodic tilings, and you can see them all over if you look at these old shrines and temples. It's something that when making mosaic tiles, somehow the artists knew about these interesting symmetries, that they could make these really interesting patterns that were challenging to the eye, that were somehow interesting and different from your usual periodic kinds of tilings. And so, as I'm sure you know, Dan Shechtman then won the Nobel Prize in Chemistry in 2011 for the discovery of quasicrystals. I'm not sure that the chemists were so thrilled about it because it's not necessarily chemistry per se. It's material science, it's physics, it's whatever it is. But I think it's not necessarily because quasicrystals are so important as a substance, as a material that you'd want to make. They are interesting, they do have technological applications. But it was more about how it just flew in the face of everything that we understood up until that time about crystals and crystallography and how complex matter could be, and change the way that we thought about things. So let's talk a little bit about symmetry and details behind quasicrystals. So when we think about, so it's all about symmetries. When we think about, if you look at these lattices here, this is a lattice of triangles, of squares, and of hexagons. And each one of them has the property that they tile the plane, meaning you can push them all together, no gaps, and just fill two-dimensional Euclidean space just fine. And here, each of these has, it's hard to see from the colors in the back, but each of these has two different colors. And so this one, there's a threefold rotational symmetry around any vertex. This one has a fourfold symmetry, meaning you have to turn it 1, 2, 3, 4 times to get back to the original picture because there's two colors. And here you have sixfold rotational symmetry because of the different colors that you have to turn it 6 times, right, through whatever that is, 30 degrees, 60 degrees, sixfold, to get back to where you started from, okay? And so these are examples of tilings with simple symmetries in the plane. But when you look at pentagons are an example of a shape that doesn't tile two-dimensional space. You cannot fit them together so that there are no gaps. This is a study of Monte Carlo simulation of hard pentagons that was done by Tanya Schilling when she worked with Don Frankel, I think when they were here at Amalf. And they looked at what was the best way to pack, and this was the best way to pack pentagons. That's the densest you could possibly pack them. But there's another way that you can arrange pentagons in a plane, and that is related to something called the golden mean. Have you guys heard of the golden mean before? The golden ratio or whatever? So it's a number. It's 1 plus the square root of 5 over 2, which is 1.61803, blah, 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 blah. That's this number. It's this magic ratio that they find in Greek, what's the word I'm looking for? Like an auditorium forms where they have a certain ratio of the foci of an ellipse that was aesthetically pleasing to the eye. And there's these there's always these ratios of length scales throughout art and architecture that if you look at the ratios, you somehow come up with this number, the golden mean. And the golden mean is the golden mean is defined as if you have two line segments together, one of length A and one of length B, and the whole thing is, of course, A plus B. If the ratio of A plus B over A is the same as the ratio, so the whole thing over A is the same as the ratio of A over B, then that particular ratio, there's just one way to do it, phi is I should have written tau, that's the golden mean. Okay, so if you draw a pentagon so that the ratio of the sides to this length here is the golden mean, then you can do the following thing. So you can take a pentagon, that pentagon with the particular size ratio of lengths of the golden mean, and you take a pentagon and you put 5 pentagons around it like that, and that makes a new pentagon. And then you take that pentagon and you put 5 pentagons like it around it. So you start with this one, and then we flipped it over, and then you put 5 more around it. And now you have this extra space, which you fill in with another pentagon, because you have this open space and you're trying to get a denser packing. And then you can take that thing and do it again and keep going. And this is something that's an example of what's called a Penrose tile that was discovered in the 70s by Roger Penrose. And eventually you can build this thing out and you see all kinds of pentagonal order. And this is what was referred to as quasiperiodicity. Because again, in this pattern, you cannot find a repeat unit. But you look at it and you say, well, clearly there's some kind of order in that pattern. This is not a random pattern, right? And so McKay wrote about these patterns as well. This is the Penrose pentagon tiling, and McKay did some work on the pentagonal snowflake. Let's see what I want to say about that. So another thing that comes up in quasicrystals is the Fibonacci series. Have you heard of the Fibonacci series? So the Fibonacci series is a sequence of numbers that starts with 1, and then you add the previous number to the current number to get the next number. So you start with 1, 1 and 0 is 1, 1 and 1 is 2, 2 and 1 is 3, 3 and 2 is 5. You keep going, and so you get this series. So here's a series here. So that's just doing it with numbers, and you get these numbers. But you can also apply that to tilings. And so, for example, if you, so this is an experiment that was done by the Beckinger group in 2008. They took a flat plane and they took colloidal particles that on their own would want to self-assemble into a hexagonal packing in 2 dimensions, just like the tightest packing that you could get of ball bearings on a surface, say. But instead of letting them do that, they shined 5 laser beams to create a 5-fold symmetric, orientationally symmetric pattern. And the colloids wanted to go where the light was, where the interference patterns were. And so they ended up getting a quasicrystalline structure by doing that. And one of the ways to analyze this structure is that they found these kinds of tilings where one colloidal particle would sit on every vertex like this. And if you look at the tilings, another way to make a Fibonacci series is that you have a rule that wherever you see, so you have these short, see these short, so this is a tiling motif with all these triangles, squares, triangles. And this is what we call long motif, which is another row of squares and another row of triangles. And you can make a quasicrystal by taking this motif, the blue one, and this motif, the green one, and putting them together in just the right order. And if you put them together in this order of where you, so you start with, say you start with a short one, and then the next one, if you see a short, the next one is a long one. And then if you see a long one, you replace it by a long one and a short one. And there's a pattern that you follow. And that pattern is the Fibonacci series. And so a Fibonacci series, it turns out, is one-dimensionally quasiperiodic. So it's like an example of a 1D quasicrystal in one dimension. So that's something that you see come up. It'll come up later when we start to analyze some of our quasicrystals. Is that one of the things you look for is this Fibonacci series of spacings between neighboring particles or between small motifs of neighboring particles. Okay, so what does all of this have to do with soft matter? Yes, please.
What is the difference exactly between quasi-periodic, like this Fibonacci series, and not periodic?
So you can be not periodic and be random or follow some other sort of rule. So the Fibonacci series, that follows a particular rule that it's not periodic, but it's generated by a rule, right? And so we call it quasiperiodic, or aperiodic is another way of saying it, which is different than something that's just random. Meaning, if it's random, there's no underlying rule that's generating it, other than something stochastic. But if you use a deterministic rule to generate something, but it's still not periodic, then you can call that aperiodic or quasiperiodic. And that's the situation in quasicrystals.
Right.
Yeah?
Is there always a starting point of this crystal? Because in the Penrose study, you start at a certain point and you build it up.
That is a great question. How do they form? We're going to talk about that later. How in the world do these things form? Yeah. I mean, so when you make one, when you build one by hand, yeah, there's a starting point. You put something down. You say, okay, now let's build off from there following some rules.
There's no unique point from which you can...
No, and in fact, what we'll talk about is that there are not necessarily unique tilings. There's different ways of generating a quasicrystal. And even from one set of diffraction data, you could in principle match different quasiperiodic tilings to the diffraction data. Yeah, we'll get into that. Are there other questions? Okay, so where does soft matter come in? So until until the early 2000s, the only quasicrystals that were known about or anybody talked about were metals, metal alloys. At least 2 components. Most of the time you need 3 components. And most quasicrystals were had this icosahedral symmetry, which we'll talk more about. And what that means is so an icosahedral quasicrystal is aperiodic or quasiperiodic in all 3 Euclidean directions. Okay. There are other quasicrystals that are only periodic in 2 dimensions, and so we'll talk about that. But so how do we get to soft matter? So we take a quick digression. Soft matter, one of the common motifs in soft materials are micelles. So micelles are what you get if you have, say, a small molecule, like called a surfactant, with a head group and a tail group that are chemically different from each other. Maybe one is oil-loving and the other water-loving. You throw them into water, and the water-loving part of the molecule is very happy. The oil-loving part of the molecule is very unhappy in water. And so these molecules will naturally start to self-assemble in such a way that it reduces the exposure of the water-hating parts to the water and increases the exposure of the water-loving parts to the water, because that lowers the overall free energy of the system. Right? So always in materials, quasicrystals as well as soft matter systems, the system is always trying to minimize the free energy. And so this is an example here of some surfactant in water, say, with an oil-loving tail and a water-loving head group. Depending on the concentration of these surfactants in water, you can get different kinds of structures of the molecules. You can get something like this, which is just what's called a micelle, which basically you have enough that it can form a closed shell, expel all the water from the inside. Then the tail groups on the inside are very happy because they don't have any water, and the whole thing is like a closed, essentially spherical object. That's a micelle. If you could also, with higher concentrations or depending on the geometry of the architecture of your molecules, you can get bilayer sheets. You can get these things called liposomes, which are inverted micelles, which is like a bilayer sheet wrapped up on itself. You see that? So that you have the water-loving head groups on the outside and the inside. So you could have water inside here, water outside here, but still the, say, oil-loving tail groups are in the middle. So a surfactant system, detergent, soaps, this is what is going on in those kinds of complex fluid systems. That is like a ubiquitous example of a micelle type forming system. You can also have this in block copolymer systems, where you have 2 long chain polymers that are chemically different, but they're bound together covalently at one point. So they have to stay together. And one of them may like the solvent, one of them will not like the solvent. And so again, they'll act like a surfactant system, only now it's the length scale is a little bit larger, because now you have longer chain molecules. Okay, Once you get this object, this kind of a micelle, it turns out that in all the soft matter quasicrystals that have been reported experimentally, well, except for one, which I'll explain, they're all made of micelles, where the micelles act like an atom. So instead of having an aluminum or a manganese atom at all these different points and making up a quasicrystal, you have an entire micelle replacing an atom. So that is completely unexpected, kind of counterintuitive. And so there's maybe a few dozen papers. I think there are fewer than a dozen reported experimental observations of quasicrystals that aren't metals. The very first one was from Unger et al. This is from Virgil Perchek's group at Penn. And this is also from, I think, Perchek's group at Penn. So they published this in Science and Nature 2003, 2004, because it was so unexpected. There they were working with dendrimers. You guys know what dendrimers are? So dendrimers are these kind of fractal molecules where you have a generation, you come out with arms, and then you have two or three more arms coming out from each arm, and more arms coming out from more arms, and then every time you do that, it's another generation. So you get this kind of koosh ball thing. And it looks like this. And if you grow them out, they're basically spherical objects. And what they found is that these dendrimer molecules, again, acted like atoms, and formed, so each one of these blobs here is a dendrimer. And they found that they arranged in a really funky pattern. That at the time they said this looks like a quasicrystal. Why? Because they looked at this and they counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They said this one isn't tenfold symmetric, tenfold orientationally symmetric like the one that Sheckman found, but instead it's 12-fold symmetric. Right? So you have these particles that have 12 neighbors around them. So those were the first reports, and those were the only ones for a while. And then this is one from Frank Bates's group that was published in Science in 2010. So you can see how rare these things are. So they publish them in these so-called higher impact glossy journals, because it's so surprising to find this. So they were working with tri-block copolymers, where one of the blocks collapsed and they formed these kinds of micelles. And here's a bigger picture. I think this is a TEM image, cryo-TEM image, where you can see these dots here. Those are micelles, and around them are a bunch of other micelles, and they make this kind of pattern. And here they're trying to draw a tiling. I'll explain that tiling in a minute. And so this is another example where these kinds of structures had not ever been seen in dendrimer systems or any kind of micellar systems. No one ever saw this kind of structure before in a block copolymer system. But again, the difference to me between the two is very minor in that they're both, whatever you start with, they're made of micelles that are arranging themselves in a pattern. And then this one was published by Fisher et al. In PNAS in 2011, where they have hydrogen bonding. They have a block copolymer, but one block is hydrogen bonding. But it collapses in water into basically a micelle again. But what's amazing about their micelle is their micelles is that they actually self-assembled not only in a 12-fold thing, a quasiperiodic structure with 12-fold rotational symmetry, but also the very first 18-fold rotational symmetry, which was unheard of, right? That you could find something like that. But their diffraction data, which is hard, it's kind of hard to see here, their diffraction data was good enough to be plausible that you could do that. We actually did some further analysis to show that it looked like they were, that it really was 18-fold symmetric. And so those are the micelle phases. I want to go back and mention this one thing here. Dmitry Talipin and Chris Murray in 2009 published what I think is the first example of quasicrystalline structures obtained from nanoparticle self-assembly. we've actually been working with Chris Murray's group since then, and they found lots more quasicrystals that we're analyzing for them and writing about. But this is an example. So if you look here, they have big particles and smaller particles. 2, 3, 4, 5, 6, 7. So you get some 7-fold and 5-fold kinds of objects there. But you'll see, so in many of these cases, the samples aren't very big, right? So it's really hard to do a large-scale analysis because you don't know if I just went bigger, would I find a repeat unit? Okay, so just to give you an example of how this works, so we actually had done a study to try to understand why do these micellar quasicrystals form. And so my student Chris did this simulation of a head group, this one bead on the top, and a tail, where the tails are attractive to each other and the head groups are not. So if you throw them in a simulation box and do molecular dynamics simulations or Monte Carlo simulations or whatever, and you cool the system down or densify the system, then at some point, in order to minimize the thermodynamic free energy of the system, it will have to they'll have to self-assemble and aggregate into some sort of structures. So the top shows an example of what they do. So they form these micelles, and they actually tend to form micelles that some of them are round, but they're not always round. Sometimes they're a little oblong. Sometimes you get a double one that splits into two. And in principle, in equilibrium, these micelles are alive, and they're squiggling, and they're moving around in the system in a Brownian sort of way. And in equilibrium, the particles will leave, individual molecules will leave a micelle, go to another micelle, and you can have equilibrium in that way. So this is an image of what we saw in our simulation box. And again, these were very big simulations. The simulations go because you need something like, say, 30 to 40 molecules to self-assemble into one micelle. And each purple blob here is a micelle. And each one of these molecules is represented by like 10, 12 beads. So if you multiply that together, it becomes a fairly large simulation. So now we can do much bigger, but back when we did this was sort of the size you could get. And we were seeing the same kind of patterns that Unger and Zhang were seeing from Penn. The exact same kinds of patterns as they saw in their dendrimer kind of system. Then we did another simulation with a different architecture. So here's one with 2 tethers, one on either side. It's like a tri-block copolymer where the middle block is collapsed. And so the green block here is attractive, is in, say, poor solvent, so wants to go on the inside, and the purple tether wants to be on the outside. Just to make a different architecture, just to make it a little bit more complicated, to make it more like the one that Frank Bates was looking at in his tri-block copolymer system. And again, you see the same kind of patterns. Each one of these green blobs is a micelle of 30 to 40 molecules inside of it, okay? And you see, again, this kind of pattern emerging. So the question is, why do these patterns emerge? Why do any patterns emerge? And why do you get these particular patterns? Yes?
Just a technical question on the simulations. I guess that there are some periodic boundary conditions on that simulations.
Yes.
Do they affect the outcome of the simulations?
Yeah, that's a great question. So whenever we do these simulations, some of them I'll show you later are not done with periodic boundary conditions, but for sure the periodic and boundary conditions can affect if you're trying to form an ordered structure where the length scale of the order exceeds that of your simulation box, then it can matter. So when we do simulations where we have objects that are ordering on a larger scale, we always let the box change its size, fluctuate in size, change its the angles between the box edges so that you can achieve any symmetry, any crystal symmetry that you want. That's what's important. So you can do periodic boundary conditions as long as you let your boundaries fluctuate and accommodate any crystal symmetry that might want to grow. So that's the kind of thing we do in some of the simulations. Another thing you can do, because letting the boundaries fluctuate like that and accommodate any crystal that wants to be, is expensive. So another thing you can do is just keep it in a cubic box and go bigger and bigger and bigger, and make sure that the pattern that you're seeing isn't affected by the size of your box or by the by the periodicity, the periodicity doesn't change as you change the size of the box. So that's another way of doing it in simulations. One of the things I'll show you later is a simulation where we do have periodic boundary conditions, but we start from a gas and the whole thing collapses in the middle, so you don't even have to worry about the periodic boundary conditions. But that's always an issue, and it always comes up, especially in something like a quasicrystal, where you want to claim that something is quasiperiodic, aperiodic, and there's no repeat unit, but you've imposed a repeat unit. It's the box size, right? So then the question is, okay, so how do you map that onto reality? And then you have to do different kinds of things, like make it go bigger, 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 allow it to be in different symmetries, and look for strain in the box. And you could also do things like scale symmetry, which I'll show you, or inflation symmetry is what I want to show. So okay, this is a collection. This is a list of the soft matter and nanoparticle. When I think about nanoparticle assembly, I call that soft matter, because when nanoparticles self-assemble, the nanoparticle itself might not be an example of a soft matter system, and its electronic properties or plasmonic properties are not something that I would consider a soft matter problem. But when nanoparticles self-assemble based on electrostatics or van der Waals interactions or hydrogen bonding between the ligands that are coating them or whatever in solution, that's a soft matter type problem, because you could apply the rules of statistical mechanics and thermodynamics to understand the assemblies that the nanoparticles are forming. So I call them all soft matter. So you'll notice that almost all of them are 12-fold. There's a 10-fold one, and then there's that 18-fold one that I mentioned here by Forster's group that was found in 2011. But there's no icosahedral quasicrystals at all. And they're all these planar axial quasicrystals. So this is what a dodecagonal quasicrystal looks like. So this is hard to see. Can you guys see it? The individual particles? Maybe you want to just turn down the light for a minute. So this is a molecular dynamics simulation of particles interacting with a pair potential that we'll talk about in a minute. So you start out with a fluid, and you cool it down, and all of a sudden it self-assembles into this structure. So this is a big three-dimensional bulk sample, and every one of these particles, these red things, is a particle. And if you see, there's all these centers, and there's 12 around them. And the 12 around them are like one is front, one is back, one is front, one is back. So that is a classic example of a dodecagonal quasicrystal, meaning it has 12-fold rotational symmetry. It's quasicrystalline in this plane, but coming out of the screen, it's periodic. Okay, so it's a different class of quasicrystal that are called planar quasicrystals or axial quasicrystals. They're almost always seen in metals, mostly binary and ternary metallic alloys, things like chromium, nickel, vanadium, nickel, silicon, tantalum, tellurium. These are classic systems that make these 12-fold orientationally ordered quasicrystals. And one of the ways that you quantify, that you characterize your quasicrystal, or you have some pattern you think, I think this is a quasicrystal. One of the things you can do is to make a tiling. So you go to the centers of all of these rings, and you draw a line from the center of one ring to the center of a neighbor ring. And then draw another line to a neighbor ring. Okay, so you just sit on the center and you draw whatever neighbors you have. You go to the first neighbor that is a center, again, of one of these rings. Okay? And then when you do that, you end up with this tiling. And you see that there are different kinds of tiles. There's lots and lots of square tiles and triangle tiles. That's the predominant one. There are also these things called shields. And there's an example of a tile called a rhomb. Okay, so in some kinds of tilings and quasicrystals, those are part of the tiling. Typically in dodecagonal quasicrystals, if it's perfect, you have a bunch of square and triangle tiles, and they come together in just the right way. And I'll show you that. So let's talk about some terminology for a second. So here's that, this is another image of that quasicrystal we were just looking at in this 3D box, and here's the tiling that we put on it. And so there's different kinds of crystal lattices that you can get that are seen in both in soft matter micellar systems sometimes, but mostly in atomic systems in metals. This one's called the A15 phase, the Z phase, and the sigma phase. They're just arrangements of atoms or particles or micelles, whatever is your elementary building block. And in the A15 phase, this is the pattern, and there are these rings, interlocking rings, and if you connect the centers of all the rings to make a tile, it's just a square tiling. So this A15 phase, which is also called the beta tungsten phase, is a square tiling. Then there's the triangle tiling called the Z phase. And again, you can see that there are always these rings around a center, rings around a center. There are always these interlocking rings. Interlocking because the neighboring rings share a couple of these atoms. Can you see that? It's kind of small. Okay, this one just happens to be triangle tiling, and this is a sigma phase. The sigma phase is a mixture of the Z phase and the A15 phase. It's a mixture of the two kinds of tiles, triangles and squares. And in the sigma phase, they come together in a perfectly ordered arrangement where you can find a repeat unit of squares and triangles and say, that's my repeat unit, I repeat it, and that's called a sigma phase. And in fact, if you go back to this phase here, it turns out that so I wrote up there approximate. It turns out that, so this picture is sheared, but if you were to unshear it, you'd see these very nice triangle and square tiles. And if you take all these rings and you connect all these, what you'd end up is with a perfect sigma phase, a perfect ordered arrangement of triangle and square tiles. And it turns out that the sigma phase is what's called the first order approximant to a dodecagonal quasicrystal, meaning that the dodecagonal quasicrystal is this aperiodic arrangement of these square and triangle tiles. But if I took the square and triangle tiles and rearranged them into something ordered with a unit cell, which might be big, but some repeat unit, then I made an approximant, meaning it approximates the quasicrystal, but it's periodic instead of aperiodic. Okay, so that's often seen in these kinds of systems. You will see, instead of the quasicrystal, you'll see this sigma phase. Instead of the dodecagonal quasicrystal, you'll see a sigma phase. Every quasicrystal has some kind of an approximant, and they have higher order approximants. So I'll show you how you construct those in a couple minutes. Okay, so I wanted to say a couple more things here. So these are the basic tiles, and dodecagonal quasicrystals and their periodic approximants are examples of what are called Frank-Kasper structures. So Frank-Kasper structures are structures like crystals, which could be periodic or aperiodic crystals, that are locally polytetrahedral. Like you see little tetrahedra all over the place if you look at arrangements of particles. And what that means is, so you know, if you take a sphere and you say, what is the best packing of spheres around my sphere? 12 spheres will come around it of the same size, right? And 12 spheres will come around a center sphere, and that's the best you can pack a sphere. That you can pack 12 spheres around a central sphere locally. If systems were driven by wanting to pack densely like that, they would just keep going, but they can't. Because if you pack in this icosahedral way, so basically when you pack the 12 spheres around an inner sphere, you make a little icosahedron. And if you keep adding to that, at some point you end up with these big gaps. and it's frustrated in three-dimensional Euclidean space. So that's why we don't have icosahedral structures all over the place. And instead, the next best thing they can do is make a face-centered cubic crystal. But in Frank-Kasper phases, and things like these quasicrystals that we're talking about, you see a lot of these local arrangements. This one's called Z12, which means you have a particle or micelle or whatever at every one of these vertices. That's the icosahedron. You can also have 14 or 15, Z14. So 14 atoms around the central atom, 15 atoms around the central atom. But if you look, you see all these local tetrahedral structures, but poly because there's multiple tetrahedral structures. Okay, so we need that terminology. Okay, so if we want to answer this question of why do these micelles form these phases, whether it's a quasicrystal or it's periodic approximate, if we want to know why would they do that anyway, it actually goes back to a problem that was posed by Kelvin back in the 1600s when Kelvin lived. It's related to something called the Kelvin problem. So the Kelvin problem, Kelvin posed this problem he said, what is the space filling? So if I have a bunch of cells and I want to push these cells together, like here's a bunch of cells that are shaped like polyhedra. What is the densest arrangement that is totally space filling that minimizes the surface area of the whole structure? So I make like a foam structure, like a, or you can think of a Voronoi construction or something like that. So I take these things and I say, what if I want to just take three-dimensional space, I want to carve it up into identical cells that span space, and I want the surface area of those cells to be the minimum possible. That was the Kelvin problem. And Kelvin said, oh, that's the body-centered cubic structure. And later, Ware and Phelan, millennia later, Ware and Phelan showed that actually the A15 phase, the square tiling phase, that's actually has a minimum surface area, has a smaller surface area than the BCC phase. Okay, what in the world does this have to do with micelles? So when you have a micelle, so here's an example of how you might image a dendrimer micelle. These micelles are packing together. They have these, they have, or even if they're not dendrimer micelles, they're any kind of micelle. They have stuff on the outside, and that stuff on the outside is getting pressed together. Okay, and so typically you'll form in micelles non-close packed structures because of that soft interaction. So we're actually going to get to this a little bit later, but the typical crystal configuration for spheres is face-centered cubic. For hard spheres with hard interactions, that's what you typically get. If you have Lennard-Jones spheres, you get FCC. So FCC is the most common crystal structure that there is. If you soften the pair potential between spheres, eventually instead of getting face-centered cubic, you get body-centered cubic. When you have these micelles, they're fuzzy like this. There's a lot of entropy in there. And so if they get too close together, they have to pay a large entropic penalty. So they want to be more open than face-centered cubic. And so you tend to see a lot of BCC and this A15 phase. They're really similar in free energy. I have free energy calculations I could show you in a minute. They're really similar in free energy. And so if you have these kind of fuzzy objects that are packing in space, it's not so surprising that you might get some open structures like a BCC or an A15 phase. Okay, and that's exactly what Zahurl and Kamian at Penn proposed. They were looking at these kind of micellar systems, and they said that the BCC and A15 structures, which is the Kelvin and the Ware-Phelan structures, that explains a lot of the phases that had been seen at the time, but it didn't explain the quasicrystals. It didn't explain the why that you should lose this long-range translational order. Okay, so I'm going to explain to you why I think that these things form why my micelles will adopt these kinds of phases, and what we learn about that in terms of entropy. So if you have a pair potential, let's say you have a pair potential that looks like this, but without this bump. So I just make a pair potential. So I knew I would keep moving this more and more. So let me just draw this here. So let's say I have a, this happens to be in class too. I'll go through like 15 markers. There we go, look at that. So let's make a pair potential between two objects, two spheres, whatever, that looks something like this. So this looks like a Lennard-Jones pair potential, 1 over r to the 6th, 1 over r to the 12th minus 1 over r to the 6th. So if you have something like that, then has this well, that's similar sort of to this shape, but without this thing. That says that there's a preferred distance between the neighbors. And that first well tends to promote local polytetrahedral ordering in systems of point particles or spheres or whatever. If you now add an oscillatory nature to it and add a bump and then go to 0, then if you place, then wherever, so this is now a penalty. So any two particles that are separated by this distance are penalized energetically, right? It raises the potential energy of the system. So they're not going to want to, you're not going to want to have particles separated by that distance in your system. And so what this does then is if you place this bump right where your second neighbor would be if you were FCC, then it inhibits FCC. It tells the system, so if the pair potential looked like this, only it might prefer FCC, but if you add this bump and you put this where the second neighbor would go, it says no, FCC is bad. So it puts frustration into the system. This is a potential that a physicist by the name of Zugatov came up with in the early 90s. We call it the Zugatov potential. Because it was the first simple kind of potential that could generate these dodecagonal quasicrystals. Right. So you could get quasicrystals, you could get approximates out of this. And in fact, the simulation that I showed you of the dodecagonal quasicrystal, the red picture with the tiling, that was made by doing a molecular dynamic simulations of a bunch of particles interacting with this pair potential. So the ground state of this is actually FCC. If you get cold enough, this just loses, and it forms FCC. But if you're at high enough temperatures, then you end up getting these kinds of quasicrystalline phases. Okay, so this potential is sometimes called the mermaid potential. David Nelson pointed out to me because it's attractive, but has a long repulsive tail. Okay, so in that system, the Zugatov liquid, and this graph, the color's not so good on here. I don't know if you could see it, but the Lennard-Jones potential that I sketched over there is shown on top of this, superimposed with the Zugatov potential. So you can see that they kind of match up, and then they deviate from one another because of that bump. And what happens is that in the Lennard-Jones fluid, you will tend to have these local polytetrahedral structures, but they become longer lived, more pronounced, and could grow larger when you have this extra bump that says don't form FCC or HCP, because I'm going to give you an energetic penalty if you do that. Then it allows it to form more and more polytetrahedral structures. That was the brilliance of Zugatov in coming up with this potential, because he said this is the simplest thing I can do that will inhibit the standard FCC and HCP from forming. And so these are a bunch of examples of what some of these polytetrahedral structures look like in the fluid. So you take the Zugatov potential, you do a molecular dynamics simulation, and you cool it down, and you get this very cold fluid. You're trying to solidify, and you'll see all these kinds of structures forming, none of which, if they grew larger and larger, would be sustainable in three-dimensional space. It's just there's all this frustration. But these are examples of these polytetrahedral clusters that you get. And these are the polytetrahedral clusters that are also seen in quasicrystals, in atomic and these molecular systems. So what we think is going on is the following, that essentially in these micellar systems, so how to say this? So this pair potential is the simplest pair potential I know of that gives or approximates thereof. There are other ones where you could do this. You can make a hard sphere square wall, go like this, go like that, and then put a bump like this. Make it really simple with squares, and that works too. But essentially, this kind of thing where you have one well and this one bump, that is the simplest thing that robustly gives you a dodecagonal quasicrystal every time. And so there must be some physics in that. So if I look at the micelle system, I can say, what is the physics in the micelle system that somehow is giving me effectively as though I have point particles with this pair potential? And so what we think is going on is that you've got these micelles, and the first, and they're trying to locally order. So there's always this tendency for spherical objects to have this local polytetrahedral ordering, but it wants to make this open structure because of this. They're squishy. They're not like hard spheres. They're squishy things, and so there's a lot of entropy. And so if they're too close packed, then you pay a huge entropic penalty. So they're going to want to be a little bit open. Okay, so that's enough to give me BCC A15 phases. But then there has to be something else going on in these systems, because we see that this alone is not enough. There has to be something more. And that something more is, we think, that you have to do something to suppress the close packing. At least that's what Zugatov potential does. So what does that mean in these micellar systems? One way to suppress close packing. So here, if you have entropy, if the system wants to do like Kelvin and what Kelvin and Ware studied, where they want to form these open structures, they can still form closed structures. But you need something else to suppress this close packing, to push them off of the preferred neighbors that would have formed, say, FCC or even BCC. And so we tested this idea by making these model little micelles. So I showed you a simulation of micelles before, where we just threw a bunch of molecules in the box. They self-assembled into micelles. The micelles self-assembled into a dodecagonal quasicrystal-like structure. So now we said, okay, let's just start with the micelles themselves, because that's a much faster simulation to do. And just put a bunch of spherical micelles in a box and play around with how much entropy, how much wiggle room is in that outer corona of the micelle. We could tune it from something super stiff to something super floppy and see what that does to the overall structure of the micelles. And so this is what our little micelles look like. So we made this rigid cage, and then we attached little beads with springs. Okay, and then we could just tune that spring constant, make it super stiff or super floppy. And what that showed us is that, so depending on how stiff that was, we could get different kinds of structures. Okay, so if we made that spring constant very stiff, then we always got an FCC structure. As soon as you start to make it more floppy, then you get BCC, and then you get A15. And one of the ways that we could see this is, so this plot here shows the decreasing stiffness, so like increasing floppiness to the right of these side groups. And this shows the relative free energy difference compared to FCC, say HCP. So whenever you want to study the stability of a structure, you always have to, so you can do all kinds of simulations and get things out that self-assemble. But you don't know if that's a free energy minimum or not. You don't know if it's thermodynamically stable or metastable relative to some other structure. If you have other candidate structures in mind, then you can compare the free energies of two structures by doing some kind of thermodynamic integration, which is what we do here, where you basically calculate the work that it would take to go from some perfect Einstein-like crystal to the crystal that you have, and from an Einstein crystal to the other candidate crystal, and you could subtract the two, and then you have the difference in the free energies between your structure and some other candidate structure. And whichever is the lowest free energy wins. So here, we're calculating that free energy difference for increased mobility, or increased floppiness. So down here, it's really stiff. The springs are really stiff. And the thing with the lowest free energy are those blue triangles and the pink triangles. And that's face-centered cubic and hexagonal close packed, which are almost the same in free energy. But FCC is just a teeny bit lower in free energy. That was something that Don Frankel showed some years ago. So when the things are super stiff, the free energy tells us that, yeah, FCC-CP is stable. But then you see that as we start to make them more floppy, make our micelles more wiggly, then all of a sudden these other structures become lower in free energy and therefore more stable. And that's A15, BCC, and a dodecagonal quasicrystal. Okay, so those structures have a lower free energy. So it's possible to calculate rigorously the free energy and show how the crossover occurs. And all we're doing is adding a little bit more entropy in the system by making the springs less stiff and the things more wiggly.
Can I ask a question?
Yeah.
So in this simulation, you didn't need this extra bump in function.
So we did a simulation with the potential, with the bump, and we got dodecagonal quasicrystal, what Zugatov had already showed. So we were able to reproduce the dodecagonal quasicrystal. Now we're taking a system where we have no pair potential. We're just throwing in surfactants, or in this case, we're building these micelles and we're throwing them in a box and letting them interact. So they're just hard particles. You have micelles and you have the little beads, and the beads are connected to the micelles, but there's no interaction of one micelle with another other than that just excluded volume. So there's no Zugatov potential in there. What we're trying to do is understand how the essential features of the Zugatov potential, which gives us a dodecagonal quasicrystal, are manifested in a soft matter system of micelles. Right? So we're not putting the potential in explicitly. We're trying to see, are there features just naturally inherent to these micellar systems that I could point to and say, oh, that's giving me the effect of the first well in Zugatov, and that thing is giving me the effect of the bump in Zugatov. If I can find those two things, then I understand why micelle systems are always forming these dodecagonal quasicrystals. Does that make sense?
Yeah, you're going to tell now what those things are.
Yes. That's what I'm doing. So, okay. So this thing, this is important. So this thing right here, all spherical micelles, we tune the mobility, and we were able to go from FCC to these more open structures. We got a lot of these polytetrahedral local structures, but on its own, we couldn't self-assemble a quasicrystal. If we set it up as a quasicrystal and calculated the free energy difference compared to something else, and if the spring was floppy, then it was a lower free energy. But just letting the micelles self-assemble on their own, we couldn't get it. So we needed something else. So we went back and asked, well, so remember, let me go find it really quick, right here. So when we did these simulations where we just threw the molecules in there and they aggregated themselves into the micelles before the micelles ordered, and we look at the sphericity of the micelles, we saw that there were most of the micelles were basically spherical, but a bunch of them are not spherical. And that happens in both cases, in either case. So there's no reason to expect that micelles are always perfectly spherical in a thermodynamic system not at zero temperature, right? You have fluctuations. So you could have some micelles that aren't spherical. So we said, well, maybe that's what's providing the effect of this bump to inhibit close packing. So we went and looked at this simulation. We said, what if we just mixed together a bunch of hard spheres and hard dimers? And so we start with spheres, then we just throw in some dimers, throw in some more, throw in some more, so they're like oblong. As soon as I throw in some oblong ones, then FCC is not going to be able to form, right? Phase center cubic's not going to be able to form, and because we're going to mess up the lattice spacing. It's just not going to work. And so when we did that, and then we again calculated now the free energy difference in such a system as a fraction versus the fraction of dimers. If we have no dimers at all, they're just spheres, and of course what comes out is FCC and HCP. But as we start to throw more and more and more dimers in, what comes out is the A15 phase and the dodecagonal quasicrystal become lower in free energy. But again, they don't self-assemble on their own. But if we put the two together, if we throw together spherical micelles with a floppy corona and some aspherical micelles, then every time out comes this dodecagonal like ordering of the quasicrystals. So if you go back to the Dendrimer case of Perchek et al., and you go back to Frank Bates's case of tri-block copolymers and to Fisher's case of block copolymers with hydrogen bonding, there are instances where the micelles aren't perfectly spherical. The micelles can be somewhat oblong. And that messes up the local packing. So there's these two things. You've got the fuzzy corona in all those cases that are trying to give you a more open packing, and you've got this other feature of the non-spherical nature, something that pushes off a lattice spacing, says even BCC is bad, even A15 is bad. And then you have enough frustration that out comes this quasicrystal structure. Let's see what else. Right. So that's what we think is going on. And it seems like this is something that you don't have to design your micellar system special. It's just if you have any soft matter system that tends to form micelles, you will always have these two things, that the micelle is a floppy object and the micelles aren't all perfectly round at the same time. And that's all you need to get this dodecagonal quasicrystal. So for us, the question is not why do we see dodecagonal quasicrystals in micelles, is why were they not seen all the time? They should always be there. And in fact, they probably are, but they weren't recognized as such because they can look messy unless you have a big sample and you can see this big pattern and you know what you're looking for. And also because it may not be the long time stable phase. It may be something that's that it's a metastable phase. Okay, so before we break, the main point that I want to make is that soft matter quasicrystals, all of them so far that I know of, are entropically stabilized. This is not typically the case for regular quasicrystals made of metals. Entropy can play a role in those systems, but in these micellar systems, it seems to be the whole ballgame, that you have a lot of entropy in these micelles. And so they're all entropically stabilized. So when we come back from break, we'll talk more detail about what is entropy, why is it so important in these systems, where is it coming from, and how can we understand that to build more complex systems. Entropy is typically taught as something that can colloquially be thought of as disorder. But that's a really bad way to think about entropy. And instead, entropy should really be thought about options, as options. So this is the Boltzmann expression for entropy, where if W is, say, the number of ways or the number of microstates in the system. Does everyone understand what I mean when I say microstates? So every possible instantiation of a system. So in this room, every possible microstate might be every possible arrangement of you guys in your chairs. That might be one, so this is one microstate. And if you two switch, that's another microstate. If you guys switch, that's another microstate. So there's all these different microstates. Then you can imagine microstates of, well, what if the chairs weren't there, but the chairs were over here? You can think about all of those. So when you think about all the degrees of freedom in the system, every possible instantiation that is thermodynamically allowed is a microstate of the system. And so if W is the number of microstates in the system, if all microstates are equally likely, then the entropy is equal to that. So if all microstates equally likely, then S is K Boltzmann times log W. So when do you have all microstates equally likely?
They have the same energy?
If they all have the same energy. In what we call a microcanonical ensemble of, you have a completely closed, utterly isolated system where nothing can go in and out. No energy, no communication, particle number, nothing. Completely isolated, closed system. All microstates are equally likely, and the entropy will tend to be to maximize in the system, and S is just KB times the log of the number of possible arrangements or number of microstates. That's the same thing as if you flip a coin and you get heads and tails, and I flip a bunch of coins. Every possible sequence of head and tails is equally likely because there's no more information in the system, there's no biasing of the system to one microstate or another. Okay, more generally, we have the Gibbs entropy law, or the Gibbs entropy rule, where the entropy is minus the sum over all microstates, the probability of microstate times the log of the probability of a microstate. So if you have a situation like in a thermal system where your system, say, is in contact with a heat bath, and so heat can flow back and forth, so you have, say, a canonical ensemble or an NVT ensemble, then the probability of a microstate depends on the energy of the microstate. And so P sub nu is something that depends on the Boltzmann factor, e to the minus beta energy of the microstate, divided by a constant, the partition function. But in the case where all the microstates are equally likely, then P sub nu is just 1 over W. The probability of any one microstate is just 1 over the number of microstates that I have, if they're all equally likely, right? And so then if I substitute 1 over W in here, I have minus sum over nu 1 over W log of 1 over W, which is, and so the minus and log 1 over W cancel each other. So I have 1 over W log W times the sum over all the microstates, but there's W microstates. So that cancels, sorry, this should be over KB. And so this ends up giving you S equals KB log W. So the Gibbs entropy formula is the most general expression that there is for entropy. S divided by KB. I always forget to write that because it's an annoying constant that we have because of, was it Clausius, Clapeyron? I never remember who introduced that constant. But when you want to make connections of entropy to information, say in information theory, that Boltzmann constant isn't there. Anyway, this is the most general, this is like the first thing that you might always write down for entropy. And then depending on the situation, you might simplify it. Okay. Regardless how you think about it, entropy is a concept that is often harder to quantify than other types of forces because it's like a statistical emergent force. And the reason why entropy is interesting and why thinking about entropy as disorder is not the right way of thinking about it is that entropy can order stuff. If there's more ways of being ordered than there are of being disordered. So if I have a system that where the system tends to maximize the entropy. Maximizing the entropy means maximizing the number of possible microstates in the system. And if there are more microstates available to the system in which the objects are ordered than disordered, then the system will order to maximize the entropy. Then that's not usually the way we think about systems. It's in many systems, it's not the case that that the more ordered things are, the higher the entropy. It's often the other way around. But in soft matter, this comes up a lot. And one of the first places this comes up is work that was done by Onsager on liquid crystals back in 1949, who recognized that if you have a bunch of rods whose aspect ratio is long enough, meaning longer than, say, 3:1, and they're hard rods, and you put no interaction energy in the system whatsoever. They're just hard particles. They just can't overlap. And this is this Monte Carlo simulation where we're just randomly moving, translating, and rotating the particles over time. When they're red, they're disordered relative to their neighbors, and we color them green as soon as there's some kind of net alignment with its neighbors. And so you see that as you run the simulation, you start out totally disordered. If the concentration is high enough in the box of rods, it'll spontaneously order, and you go from a isotropic to a pneumatic system phase of liquid crystals. And so the reason why this happens, and this is what Onsager showed, is that the system, they get so close that they realize that if they want to keep their rotational symmetry, they can only pack so close. So the system gives up rotational symmetry in order to gain more translational degrees of freedom. It gives up rotation to gain translation. And because there are more microstates available to the system, so this is microstate, this one, these are all different microstates, all the different ways you can do this, then if they have their full degree of rotation, then they'll get jammed up. And that's all the physics there is behind an isotropic to pneumatic transition. It's a completely entropically driven transition. So that's not so weird when we think about rods. We get it. You push them together, they can't line up, so they're going to line up, and then they have more room. That makes sense. But it's also true of spheres. And that was something that was proposed by the chemist Kirkwood back in the 50s, and then his student at the time, Bernie Alder, working with Wainwright, did the very first molecular dynamics simulation of hard particles ever in 57. And Kirkwood's other student, Wood, did the first Monte Carlo simulation ever of the exact same system. And both of them showed that if you just put hard spheres in a box, just like Onsager's rods, but now they're spheres, there's no interaction energy, there's no pair potential, they're just hard particles. As soon as you get to 50% packing fraction, they go from being disordered to being ordered. And when they're green, that shows local FCC ordering. And you can see it starts to get green, and then the whole box is green. And that's because there are more microstates available to the system where the particles look like this than when they look like this. Now that seems totally counterintuitive. But that's because if I take this sphere and move it a little this way, a little this way, a little this way, each one of those is a different microstate. But it's still consistent with a crystal, right? So these particles are moving around, say they're colloids and solvent. They're moving around, they're Brownian spheres moving around. And they can move a lot and still be consistent with a crystal. So it turns out that if the spheres don't order, then they'll hit a random close packing transition at, I think, something like 63% or 67. I can't remember the number right now. They cannot pack any denser. They'll just jam. But if you all of a sudden arrange them like FCC, you can actually pack them to 74.05%. So there's a ton more room in the system. You get up to this point, and it's like they're stuck, and then you say, okay, well, let me organize you. You get all this extra room in the system. And all that extra free volume in the system means more possible microstates, more places to put the particles. So that's so counterintuitive that for decades it was something argued vehemently at Gordon conferences and throughout the physics and chemistry community, saying that just makes no sense, that's just crazy. Of course it was shown by a computer simulation, but back then that was not enough to convince everybody. And so it took until, I think sometime in the 80s, for Pusey and Chaikin and others to actually do the experiments and show that hard sphere colloids crystallize. So before we ever got, the first time that I ever started thinking about quasicrystals was completely by accident, because we were studying hard tetrahedra. So just tetrahedrally shaped objects, threw them in a box, just like the hard sphere simulation, did a Monte Carlo simulation of hard tetrahedra, and out came something that looked like this. This is about 13,000 particles, and we said, okay, well that looks like something. And we didn't know what it was, so we sliced and diced it, looked at it different ways. And if you were to, so if you call this, you put in some axes, X, Y, Z, orthogonal axes, and then you turn it and you look at it down in the XY plane, then it looks like this. But I still couldn't see anything, so I asked the student to make them translucent, so I could see through the whole box. Because I thought, if there's some kind of order, then somehow these edges should all line up. And so then we get something that looks like this. So you can start to see the edges are lining up, and you start to see these wheels. And it turns out that this thing has 12-fold rotational symmetry. And that was a big surprise, because until we had done this study, hard tetrahedra were not known or thought to self-assemble just due to entropy into anything. And it turned out that they formed this very complicated structure. If you turn it on its side, so remember we said that the dodecagonal quasicrystal is quasiperiodic in a plane, but periodic in the third direction. So from the side, what this actually looks like is a bunch of pentagonal dipyramids. So 5, I don't need these anymore, 5 tetrahedra together in a little wheel, and then 12 of them up, down, up, down, up, down to make a ring. Pentagonal dipyramid sits in a ring, then there's another pentagonal dipyramid, another ring, keeps going, and each one of these logs is one of those things. So these logs that you're seeing here are the 12-member rings, up, down, that go around. And then in between each of these, but it's hard to see, is one of these little caps. These 5-member little pentagonal dipyramids. So the system starts out completely disordered, a fluid, a 50% packing fraction. Just sit there, do a Monte Carlo simulation. Just randomly choose a particle, try to rotate or translate it. If they overlap, you reject the move. If it doesn't overlap, you accept the move. That's it. And out comes this complicated thing. So they form these logs, and the logs tilt a little like this, because it turns out that they have more entropy that way. And then dimers of tetrahedra come in and fill in the interstices. It's the most complicated structure I've ever seen in my life. This is what the scattering pattern and something called the bond order diagram look like. So the first thing was we calculated the scattering pattern. And we started counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And every one of these rings has another 12 spots, another 12 spots. So that confirmed this suspicion that, yep, this is some sort of 12-fold coordinated thing. And then this is looking at it from the periodic directions, and you see that you don't have this aperiodicity or quasiperiodicity in the other direction. These things at the top, we use that a lot in our analysis. They're called bond order diagrams, and I'll show you some other images of bond order diagrams. All they mean is you stand on a particle. So for us, when we stand on a particle, we stand on the center of mass of the particle and don't care about where the corners are. So you stand in the center of mass of a tetrahedron, and then you look for the other centers of mass of the other tetrahedra in your first neighbor shell, and then you draw a spot on the unit sphere. And that's and so you can project the first neighbor shell onto the surface of a unit sphere. You can also do second neighbor shell, third neighbor shells. And so if the system is completely random, and there's no orientational order between the particles, no correlation between the positions of the particles, then you just see white noise on your sphere. Instead, if you see a pattern, that tells you that there's some order in the system. So this is what the pattern looks like for a dodecagonal quasicrystal. If this sharpens up a little, you'd start to see these dots. But at the time, that was the best we could do. But that's like a really quick and dirty way of seeing if you have some order in your system. So you do that for every single particle in your system, and then you just superimpose all your bond order, all the statistics for all the little spheres onto one sphere. That's how you do that. So this is what the whole image looks like, completely see-through. I think that's cool. It looks like stained glass. And this is what the structure looks like. This is looking at it from the top down, and these are the pentagonal dipyramids, and those are the 12-member rings. And so, as far as we know, this is the first. It's the first example of a dodecagonal quasicrystal for purely hard particles, for tetrahedra. This is an example. So this is that same simulation, just to show you. I'm not showing you all the tetrahedra that don't, in the end, come together into one log, just so you can see that they're all over the place. There's a ton of motion in the system. It's only 50% of box is full. 50% of it is empty, and you can see how far they end up moving, and then they just form this. They just form.
Any other interaction except repulsion?
Correct. There's nothing. It's just entropy. So that simulation there is what got me obsessed with entropy and convinced me that I did not understand it the way that I wanted and needed to understand entropy. Because this shows you that entropy is, I mean, it's clear that, so this is, say, an NVT simulation. In an NVT system, a canonical or isothermal system, the Helmholtz free energy F is equal to potential energy minus T times S. And so if the system is going to minimize F, but now I don't have any pair potential. I just don't allow any interaction. So now it's just always 0. So all I have is this minus TS SERP. So if I'm going to minimize the free energy, I have to maximize the entropy. And so there's nothing else going on in the system. If we go back to the case of the micelles, at the end of the day, those micelles, once the micelles, there's all kinds of interactions in the intermolecular interactions between the diabollical polymers or the surfactants and the water and whatever. But at the end of the day, you end up with these micelles, and the micelle interactions are very weak. All the interactions kind of inside to make the micelle. The micelles themselves, the outer parts of the micelles are in good solvent. They're happy like that. So it's like they're hard particles, but not hard, maybe soft. And we saw that they're kind of squishy particles. So entropy is, in the end of the day, what's ordering those micelles too. So this is just like stripped down to its bare essence. Just put particles, spheres, rods, tetrahedra, whatever shapes in a box. So I'm sure, one of the leading groups in the Netherlands, Marilyn Dijkstra's group, are any of you guys in that group? There you are. You guys are like the leading group doing, these kinds of simulations in the Netherlands. So are you guys giving talks on this? If you want to see like hard particles of different shapes self-assembling into different crystal structures, there's between your group and our group and a few other groups, we've studied thousands of shapes now, and seen when entropy can order things like this. But so far, with purely hard shapes, we've not found anything more complicated than this crazy dodecagonal quasicrystal. And it turns out that our quasicrystal is isostructural to the tantalum-tellurium quasicrystal, which is a chalcogenide. So this is an experiment that was published in 1998 of a tantalum and tellurium system. This is where the tantalum and tellurium atoms all sit. And then if you connect all the dots, connect all the atoms, you end up with something like this. This is what their, this is their scattering pattern. This is their scattering pattern rotated so that we can line it up with ours. And we see that peak for peak for peak, that they all sit right on top of one another. So we actually have the same dodecagonal quasicrystal. And if you do the tiling, you see all these rings, interconnected rings all over the place, and then you connect the dots, make the tiles, you see this square triangle all over the place, right? And so you can see it's a similar type of thing. Now, I mentioned that the dodecagonal quasicrystals are always described by these square triangle tiles, but there's lots of different ways you can decorate, what's called decorate the tiling, decorate the lattice. So you could have all, oh my God, I thought that was a wall. I actually gave a talk a couple of weeks ago at Michigan in this round auditorium, this old amphitheater round auditorium. And I'm standing there while they're introducing me, and I lean against the wall, only it wasn't a wall, it was a door that was open. That was a bummer. Anyway, you can actually decorate these tilings. So you can get these dodecagonal quasicrystals can get crazy, crazy, crazy complicated, but still at the end of the day be described by a type of tiling like this. So here's our tetrahedron quasicrystal. And so looking down in this sort of in a dual representation, and then connecting the dots, and you can see this kind of tiling. And this is what makes up the tiles. So underlying the tiling are particles. And so here's our pentagonal dipyramid in these 12-member rings. And then there's other ones that, I mentioned that there's other ones that fill up the interstices that just go there, because that's the way to maximize the entropy of the structure. So this is the triangle tile, and that's the square tile. And those things are basically arranged randomly in this system. What's also cool about this particular quasicrystal is that, so in addition to being made up of all these square and triangle tilings, if you so you look down at a log and you take one tetrahedron and you just go out, you come out, there's a spiral, a tetrahelix like this. So here's a tetrahelix, and here's another one, and here's another one. And so, do you guys know this expression of Lincoln logs? Lincoln logs, they're like these, they're logs with cutouts, and they all fit together and make a cabin. Okay, anyway, the whole system is made up of these interconnected tetrahelices. So if you come out of, so you have these logs are defined by these 12-member rings. So you actually have 12 tetrahelices coming out. And going through every log, every particle is part of one or more tetrahelix. And so it goes right-handed, left-handed, right-handed, left-handed. So the whole thing overall isn't chiral. But there's all kinds of amazing structure in here that's all figured out, that's all a result of entropy maximization. So I mentioned before this periodic approximate. I said if you could separate the tiles and put them back together in an ordered way, then you'd make what's called an approximate to a quasicrystal. So this is an example of the simplest or the first order approximate to our dodecagonal quasicrystal is to take the tiles and put them together like this. So you can see that here's a square. So if I connect the dots between the centers of the pentagonal dipyramid, there's a square tile, and here's a triangle tile here, and there's another square tile. And so you can see how you can start to draw the tiling. So if I overlay it like that, so there's the tiling superimposed on top. So now you see the triangle and square, and it's called a 3-4-3-2-4 Archimedean tiling. So if I go around, like let's say I pick this vertex right here. I have a triangle, a square, a triangle, triangle, square. So that's triangle is 3, square is 4, 2 3s, or 3 squared, and another 4. So Archimedean tilings, there's 11 of them. Archimedean tilings are tilings that span space for which there's only one kind of vertex. So like a square grid is an Archimedean tiling. It's just, each vertex is a square, 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 square. So it's just 4 to the 4. And this one is the 3, 4, 3, 2, 4 Archimedean tiling, which is also the sigma phase. I just didn't point that out before. The sigma phase is a 3, 2, 4, 3, 4, 3, 2, 4 Archimedean tiling. So what's important about this is it's a completely different symmetry. It's got fourfold rotational symmetry as soon as you make the sigma phase. So you can see it. Once you get the diffraction pattern, it looks similar, very similar to the icosahedral, to the dodecagonal quasicrystal, but you can see that there's fourfold symmetry instead of 12-fold symmetry as soon as you get the approximate. So if you have good enough data, which is really hard to get in experiments on soft matter systems because you need so many micelles, and the system is noisy. So we have to do these really big simulations in order to get enough statistics to get so many rings with such clarity that we can actually tell the difference between fourfold symmetric and 12-fold symmetric in that scattering pattern. But you can, and so you can see that there's this difference. And what's interesting is that the nearest periodic approximate has 82 particles in the unit cell. So the approximate has a lower free energy than the quasicrystal does. But it takes so long for the system to order because there are 82 particles in the unit cell. The whole thing would have to organize. And so kinetically, it's very hard to see the equilibration into the approximate. Here's what the two different tilings look like. So this is the tiling I was just showing you, where it's every vertex is identical. And here's the tiling for the quasicrystal. And the other thing you notice is that the ratio of triangle to square tilings is different. Yes. Were you scratching? Okay, sorry. The ratio of triangle to square tilings is different in a quasicrystal to an approximate. So that's another thing you can do in your system. If you have a system and you say, is this a quasicrystal or not? I don't know. You could start making your tiling. You start to count how many different kinds of vertices do I have in my tiling? How many triangle tiles do I have? What is the ratio of triangle to square tiles? If it's closer to 2, then you probably have a sigma phase. If it's closer to 2.4, then you may actually have a quasicrystal. So in addition to looking at things in the bond order diagram and the diffraction pattern, you can do a lot of real space analysis to see what it is that you have, as long as you have clean enough data. Now, it turns out that, so when we talk about ground states in any kind of a system, we talk about a ground state. Usually we mean like the ground state, like the 0 temperature ground state of a system. And if we're not at 0 temperature, we're at some finite temperature, then the system is so if we just have a liquid or something like that, or any kind of a solid or crystal, and we say we're at some temperature, and so we're not in the ground state. But we can ask, what's the ground state structure versus the structure that I'm at some finite temperature, where entropy may play more of a role? And sometimes the structure of any crystal at non-zero temperatures is the same as the ground state crystal structure, and sometimes it's different. In these hard particle systems, the equivalent to the ground state structure, instead of T equals 0, it's the infinite pressure structure. It's the densest packing limit structure. That's the thing that minimizes the Gibbs free energy, is the densest possible structure. And so when we ask what's the ground state equivalent, we say, well, what's the densest packing? And it turns out that the densest packing of tetrahedra is not the quasicrystal and not the approximate, although we thought so for like a month back in November or October of 2009, until this paper came out by Callis, Elser, and Gravel on the archive that showed that a much simpler arrangement of tetrahedra, where you took 2 tetrahedra, put them like that, and now you have a dimer, and you take another dimer, because they're antisymmetric, and put it like that, that's your unit cell. That's it. 4 particle unit cell. So they constructed this and showed that you could actually pack it to a density of 85.46, whereas the densest we were able to pack our approximate was something like 84 something. So this was denser. So that means that's the ground state structure. Now it turns out that they had it almost right, but not quite right. They had the unit cell right, but the symmetry of the lattice wasn't quite right. And so we found that instead of their symmetry, you just tweak them a little bit, and you actually get a denser structure that packs at 85.6347%. And that is the densest packing. So if you're ever on, like, I don't know, Jeopardy or some game show, and someone asks you, what's the densest you can possibly pack hard tetrahedron in a box, you say 85.6347%. Okay, but it basically looks like this. So that means that in the infinite pressure limit, that's the thermodynamically favored structure. I may never be able to self-assemble it, but I know that that's a thermodynamic ground state of the system. So let's say I build my system like that, and now I start to expand the box and let there be a little more room, a little bit more room. It's like going up in temperature for an enthalpic crystal. So I'd start to give it more room. What happens to that structure? What we do is we don't start from the densest structure and expand the box. We just start from a dense fluid of particles and let it assemble into whatever it wants. And never, ever does it assemble that thing. It always assembles the quasicrystal. So then you can ask the question, so does that mean that the quasicrystal or its approximate is thermodynamically favored at the densities we're at, and later there should be a thermodynamic transition to this thing? Or are these states metastable? And it always wants to be this, but kinetically it just can't figure it out. Although then why would it, like, to form, the fact that it could form something whose nearest periodic approximate has 82 particles in the unit cell seems to me harder than to make this thing with 4 particles in the unit cell. So you can calculate the free energy of the systems. And so you could look, for example, at the packing fraction as a function of the pressure. So if you look at that top curve, that's an equation of state. It says if my system is, so every point along that is thermodynamically equilibrated. So you say, at this packing fraction, what's the pressure? And now I increase the packing fraction, what's the new pressure? Increase, what's the new pressure? And so you make all those curves. And the blue is the dimer crystal, the red is the approximate, which we always have to build because we don't get it in our simulation, and the quasicrystal that we always get over and over in our simulation. And then the blow up there, so you can see that part right there is blown up, and that's where the phase transition is, right? That's where it goes from a fluid to a quasicrystal. And then then you see the top part. So if you look, here, this takes the free energy difference between the quasicrystal and the dimer crystal as a function of pressure. And what it shows is that, which one is this? This is delta G, so this must be dimer minus quasicrystal. So this says that the quasicrystal, or its approximate, is thermodynamically stable at all pressures up to here. And then the dimer crystal becomes thermodynamically more stable. But if I look at that pressure and I look up there and I say, oh, that's a really high pressure, what does the packing fraction have to be to get that pressure? It has to be 80% packing fraction. So that's why we never ever see it, because it's just not thermodynamically stable at packing fractions below 80%, and we would never be able to equilibrate something beyond, say, 75% packing fraction. You'd have to just wait forever. And I don't think that that's just true of simulation. That's true of an experiment on hard particle colloids in solution as well. If you have it so densely packed that it's like 75, 80%, 85%, or here in this case 84% packing fraction, the kinetics are so slow. You would just never see it order into that. But this shows you how you would go about, like, if you get a system, if you do a simulation, you self-assemble something, and you say, wow, is that this thermodynamically stable state? You can never know for sure that it's thermodynamically stable. You can know that it's not because you watch it, and ping, it changes into something else. And you go, oh, it was metastable. But if it doesn't ever change into anything, all you can know is that it's persistent, it's stable. And if you have a candidate structure that you can compare the free energy to, you can say whether or not it's stable relative to that other thing. But you don't know whether or not it's unstable relative to something that you haven't tried. That's just the way it is, right? So you know, there are certain things that you can think of to try. If no one had found this dimer crystal, we would never have thought, no one would ever have thought to try it against something. We wouldn't know what to try it against. But at least now the dimer crystal is something to try it against, and it shows that in principle the tetrahedron phase diagram is really pretty complicated because it goes from this quasicrystal approximate type phase to this dimer crystal. So we had this brilliant idea, and we said, well, so somehow at all of these pressures and packing fractions lower than here, the system maximizes its entropy through the quasicrystal rather than the dimer phase. So what if we reduce some of the degrees of freedom and favor dimers by taking all our tetrahedra and gluing them together in pairs and just throwing hard dimers in the box? Surely then it will self-assemble into the dimer crystal, because we've removed a lot of the entropy. I mean, you know, there's still entropy of the dimers, but now there's, you know, there's half as many particles in the system in principle, right? Because we've glued all the pairs together. So we've removed a bunch of entropy from the system, and we favored the motif that the dimer crystal wants. But we still can't get the dimer crystal. Instead, we get back out exactly the same quasicrystal that we got before. If you look at it from the point of view of the individual tetrahedral particles, you can't tell the difference between the original quasicrystal and this one made of dimers. Only if you start to look at the dimers, you see that they can point all these different ways. So it's like a degenerate quasicrystal, because you could take your tetrahedral, you could take your dimers and point them in all sorts of different ways. And so that's interesting that still, like this quasicrystal phase, which used to be so hard to see, so hard to get, seems to be so robust in this kind of system. So we're still trying to understand why the dodecahedral quasicrystal is so preferred in tetrahedra. Clearly, we know that when systems have tendency towards local polytetrahedral ordering, they tend to form quasicrystals, like icosahedral quasicrystals and dodecagonal quasicrystals. And since we have tetrahedra, by default, we are promoting locally tetrahedral coordination. But that still doesn't explain exactly why we see this structure that we get. And so we're still trying to understand that. The main thing that is really also, you know, very puzzling to me is that there has never been a report of an icosahedral quasicrystal in a soft matter system. That's the one that the crystallographers, you know, the quasicrystal guys call the real quasicrystal, because it's quasiperiodic in all three directions. It's not just a planar. All the other ones, the 8-fold, the 10-fold, the 18-fold, the 12-fold, those are all quasicrystalline in a plane and periodic in the third direction. The icosahedral quasicrystal is the only one in all three directions. It is also the one that's most commonly seen in metal systems. So if you take alloys, you most of the time you do get an icosahedral quasicrystal. So, you know, why is that? The other reason why it'd be interesting to have an icosahedral quasicrystal is if you talk to quasicrystal metallurgists, there are a lot of theories as to why you get quasicrystals. What are the interactions between the atomic elements that give this to you? And it's typically thought that you have complex quantum mechanical interactions, metallic bonding, and all sorts of details like that that make it possible to get these icosahedral quasicrystals. And the lack of ever seeing them in any kind of a soft matter system where entropy is really driving things suggests that maybe that maybe that's the case, that you just need much more complex interparticle interactions to see it. There's, like I said, there's so many instances of icosahedral quasicrystals found in the lab, but they're always interrogated with scattering. And so you have all sorts of diffraction patterns, but diffraction patterns aren't unique because you never have infinite resolution. So they're not unique. And so from a diffraction pattern, one builds a real space model. But there could be a couple of real space models that are both consistent with the same diffraction pattern since it's not infinitely resolved. And so you don't know which is the right real space model. So, you know, many people build these real space models and try to understand if they're the model of a particular icosahedral quasicrystal. There have been many attempts to do simulations of, you know, aluminum, manganese, or other systems with detailed, like embedded atom type pair potentials where you have an aluminum-aluminum interaction, you know, a pair potential that's much more complicated than this, with Friedel oscillations and you know, a very long range interaction that you would expect for a system undergoing metallic bonding, where they have aluminum-aluminum, aluminum-manganese, manganese-manganese interactions. So you have all the different interactions. Many people have done simulations of those, never produced a quasicrystal. Instead, they build a quasicrystal and then figure out the pair potentials that make it stable, but nobody's ever self-assembled an icosahedral quasicrystal in a simulation. And one more thing is that I mentioned before that they have a photonic band gap. So this is something that was actually, I think they used some I forgot how they built this thing. So this was work done by Steinhardt and Chaikin, where they did experimental measurement of photonic properties of an icosahedral quasicrystal. So they basically built this quasicrystal and then scattered off of it and looked at the photonic spectrum and saw that it has a complete three-dimensional photonic band gap in all 3 dimensions, which means there's a clear gap with where certain wavelengths are just forbidden to pass, right? And so that's interesting for optical things if you want to have like fiber optics or things like that where you want to trap certain wavelengths inside of a waveguide. So that's another reason why it would be interesting to have quasicrystals that are not made of atoms, icosahedral quasicrystals not made of atoms, but even made of colloids with spacings that are on the wavelength of light, of visible light, because then you could actually do something interesting with that. So we studied this pair potential, and so this shows 3 different pair potentials. There's V1, V2, V3. They're just slightly shifted from one another. All of them look like this. They have one well and then a bump. And so you might think that first part is like the Zukatov potential squeezed in. And then there's another well, another bump, and another well, and another bump. So it just goes on and on. So you take this oscillatory pair potential, and then you can cut it off somewhere. And so if you look at the blue one, we have 1 well, 2 wells, 3 wells, and it's cut right there. And the green one's cut there, and the red one's cut there. So for all of these 3 pair potentials, which are practically the same but just stretched out a little bit, they all have 1, 2, 3 wells, and they're cut off right here at 0, where the potential is 0. Which means that you can so you imagine you have point particles interacting with that one of those 3 pair potentials. And so you can do this in a big box with periodic boundary conditions, but you can do it at 0 pressure because of the nature of the interaction. And it's a long story to explain how we got to this, but it turns out that these pair potentials give an icosahedral quasicrystal for the first time ever. So this just came out this month, in this month's Nature Materials. Is this one component icosahedral quasicrystal, which is so the first time it's been self-assembled in a simulation, and it's with one component, just one type of particle, and one interaction between the one type of particle. So we are going to play with the interaction to see how sensitive it is, so I'm going to show you several different ones. But it turns out that this pair potential gives you, or pair potential that looks like this gives you an icosahedral quasicrystal. What we found to be important is that the ratio of these two wells, which is what, this is what's saying, this is where, roughly where I want my first neighbor shell to be. And then I don't want any particles at that position where the peak is, or I want to really inhibit that. And then I'd like my second neighbor shell to be somewhere around here, and my third neighbor shell to be somewhere around here. The ratio of this distance to that distance is the golden mean. So if we had been smart, we would have just built this thing. We said, you know, let's just build a pair potential that has a golden mean and favors this. But we did not engineer the pair potential, as much as I'd like to say that we did. Instead, we found it by accident. And so let me just show you what it looks like. So this is a simulation, 20,000 particles in a box, molecular dynamics simulation using our GPU code HUMDY Blue, which is super fast. And the blue color indicates that it's on the outside of the quasi. It's not crystalline yet, and everything in green is nicely crystalline. And then this is showing you, it's just starting to connect bonds. These are particles. Each red one is a particle, and then this is drawing bonds between them, so you could start to see a pattern. What's really cool about this is that because of the attractive nature of the pair potential, unlike with hard particle systems that you always have to have them under pressure, right? If you always have to confine them to fix the volume, otherwise there's no interaction, they'll just fly all apart. If I threw a bunch of hard particles in a room, they'd fly apart. So you have to confine them. Here, you don't have to confine anything. So we start out with a gas, we lower the temperature, it condenses, and then starts to grow out from the center into this icosahedral quasicrystal. So here's what the scattering patterns look like. These are experimental quality, high resolution, would make a crystallographer weep diffraction pattern. Along the 5-fold axis, the 3-fold axis, and the 2-fold rotational symmetric axis. And you could see, you know, how sharp these different peaks are. This is a reconstruction of it, where once we figured out what the model was for the icosahedral quasicrystal, meaning exactly where all the atoms are in relationship to all the other atoms, then we built this just to see what it looked like. And so that's what the ideal perfect one would look like. And what we did is, so I didn't show you this expression. So this pair potential is called, well, it's called the oscillating pair potential. Chris Henley and Mikhailovich, Chris Henley's at Cornell, they came up with an empirical oscillating pair potential, which just means they said, I just want a pair potential that's oscillating. I'll just write one down. It's empirical. And then we said, okay, let's modify that a little bit. And we played around with it. And so the form of the pair potential that we end up using looks like this. It's got a 1 over r to the 15th to give you this really steep beginning so that there's a hardcore interaction. And then it's got 1 over r cubed and a cosine term with this parameter k and phi. And so those are the two parameters you can tune in your potential. You can tune, that's what I'm going to show you next. So you can tune k, that wave vector k, and you can tune that phase shift phi. And every time you do that, you're altering the potential a little bit. You're pulling the wells down, you're pulling them out like this. And if we do that, then you can make like a phase diagram where for every instantiation of phi and k, you can say, what's the phase? What's the phase? What do I get? What structure do I get? And so you get all these different kinds of structures. So everything that's pink in here are quasicrystals. So it's really robust. And then around it are all these other phases. So if I shrink it down and now show you all the phases, These are all the different structures that we get in addition to the quasicrystal when we tune the pair potential. So in every one of these plots, the blue curve is the pair potential for that value of K and that value of phi. So that's what the pair potential looks like. You see that it always has 3 wells. But sometimes the first well is higher relative to the second well. Sometimes it's a little lower. Sometimes the width of the second well is a little narrower. Sometimes it's a little broader. This one has a really deep first well. This one has a really deep first well compared to second well. That one, the first well is even deeper than the second well. And then the first well becomes just barely like a little bump here, like a little dip first. Okay, so that's what you're, so with this one parameterization, this one expression and these 2 parameters, you can tune between all of those things. So, I mean, if you were studying one system, you wouldn't do that. You'd say, I want to study this system, and you would develop a pair potential for that one system. So this is kind of like a materials design approach, where you say, well, imagine that I can vary my system, and I want to see for what pair potential, for what shapes of pair potential do I get a really cool structure, and then I'll figure out what materials will fit that and give me that structure. So it's an inverse design kind of approach. And so we get all these different kinds of structures. These are clathrates. You study clathrates. So these are clathrates down here. These are all these very open, complex structures with complex unit cells to them. And then all in here is this quasicrystal, and then right there, separated from this whole stability field of quasicrystals, with all these other complex phases surrounding it, is the sweet spot for our quasicrystal. We have no idea why yet. This is where it just grows beautifully every time, super fast. And the rest of them grow, but why it's separated from the rest, I have no idea. I was just going to point out that here we have this A15 phase and the Z phase, which are those other phases that we saw before, which are approximants to 2-dimensional dodecagonal quasicrystals. Those also fall out of this. So originally we were trying to come up with a potential that our colloid synthesis friends could make. We said we want to get we want to get complex structures. We had given up hope of actually finding the icosahedral quasicrystal on purpose. I mean, we were trying always, but we didn't really have a plan. But we were trying to make open, complex structures from colloids where you could imagine using ligands or DNA or proteins or other things to set preferred distances. So most colloid scientists would look at these pair potentials and go, oh, we can't make that. You have 1 well, 2 wells, 3 wells. And every time we put 1 well, with the other well, we can't like separate the interactions. It's difficult to do. So we were hoping to get down to 2 wells. We're not there yet because we got sidetracked by finding an icosahedral quasicrystal. But we're trying to see if one can simplify the pair potential and still get these really complex open phases. So just to show you some analysis of this quasicrystal. So I mentioned there's a stability phase, and they were labeled LD, HD, ID. Are we supposed to stop? What time do we end? At 10? Oh my God. What? At 10 o'clock?
Yes.
Okay, I'll finish up really quick then. Remember that Penrose tiling I was showing before, where you take a pentagon with the golden, characterized by the golden mean, and you surround a pentagon by 5 pentagons, and you take that thing, and that is what this is. So you take see, there's a pentagon. So these are all our atoms in green. Then you connect them, and then you end up with a pentagon, and then there's the pentagons all around it, and then you tile those things. And if you take cuts through, you get a Fibonacci sequence of the spacing of the particles. This is another way that you can look for to see if you have a quasicrystal is to look for self-similarity. As you go bigger, 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 do you see, I think it's called inflation symmetry. Do you see the same thing on bigger and bigger and bigger scales, like in that Penrose tiling? So that's something that we also see here. So this is a bigger version of it. I think this is for not 20,000 particles, but 100,000 particles. And if you were to make a Fourier filtered image, which approximate like a high resolution electron microscopy pattern, this is what you would expect. This is what you would look for if you were an experimentalist trying to get, to get that pattern. So I will say just one more thing, which is, so one of the things that we did, let me just see if I can show it really quick. If you're interested in finding out more of this, is, so with our paper so in the SI you can click on this link from the Nature paper, from the Nature Materials paper, and get this web interface JavaScript where you can read in our data and you could turn it around, and you can do things like you can show the particles or shrink the particles, you can show the bonds between the particles and not show the particles, so then you can start to turn it around and look for the different planes. I'm not quite getting the cool projection yet. But this is also showing the bond orientational order diagram that I explained before. And now you're just turning it around so you can look for these different patterns. And then down here is the diffraction pattern along whatever direction I'm aligning it. So it's calculating that on the fly for you too. And also in this nice little applet, I want to call it applet, it's on applet. You can also pull down all the different quasicrystals, some approximants, all these other phases like the clathrate phases. You can read all that in, which I think is really nice. As simulators, we have so much data, and we publish like static pictures. I'm hoping that we can do more of this in the future so people can actually see it. Because when you're making these three-dimensional structures, I mean, I can't even see it unless I'm like inside it. And so this is a way of learning how to calculate the diffraction patterns, bond order diagrams, and things. Okay. So that link is in the paper for anyone who's interested. Let me just finish up because we're going really late, and I want to say one more thing because. Was it Kasper? You asked me the question, how do they grow? How do these things grow? So, quickly. The classical nucleation picture of crystal growth, which who knows if that's even right anyway, for regular old crystals, that's still a topic of a lot of debate, is really pretty simple. You have a fluid, a liquid, a gas, whatever, and you quench it to a temperature, pressure, where that is no longer the thermodynamic stable state. The crystal is the thermodynamic stable state. And the system is now unstable or metastable, and it's fluctuating around, and it's sampling phase space, and it hasn't yet realized that the state it's in is not the thermodynamically stable state. And what typically has to happen is that there needs to be a fluctuation in the system of a cluster of particles that is an arrangement such that the free energy of that is now lower than the rest of the system. So basically it's described by these two terms, a volume term and a surface term. And as soon as the volume term that lowers the free energy exceeds the surface term, then that thing will grow, and that's called the critical nucleus. So you have all over the place, you have these fluctuations, and at some point the nucleus gets big enough and it takes over the whole system. And so you go from a fluid, you nucleate something, eventually you end up with a solid, and so this is a picture of an entropic, this is a system of hard octahedra. It starts out fluid, and this is in the middle of the nucleus has grown, the critical nucleus has been exceeded, and now the crystal is growing from a point. So that's homogeneous nucleation, meaning that the system, you don't have nucleation sites all over the place, and you're not nucleating from a wall or from a surface. It's just starting to grow, and it grows out from one seed if you're lucky, and then you just watch it overtake the whole system, just like those spheres crystallize into FCC. Where did I put that movie? Okay, so the point is, yes.
One short question.
Yes.
You said if you're lucky, it grows from one seed. What happens if it grows from two?
So it's not that you're unlucky. It means if you want to study homogeneous nucleation, then your system is just the right size, and you've picked the quench step just right, that it doesn't nucleate everywhere, and you could just watch the process cleanly. So typically, if you do any kind of transition path sampling, umbrella sampling, transition interface sampling, these sampling methods that are designed to sample rare events like the nucleation of the critical nucleus, that's a rare event. You have to wait for that to happen to get over the energy barrier. When you're doing that, it messes it up if you have more than one growing thing in the system at one time. So that's why you'd like to just have the one. Okay, the point is, if you're growing a crystal, it's growing from inside, and so even here, when you look at this image here, there's this crystal that's growing. There's a front here. It's growing into the fluid. Typically, if you look at what's happening, the outer particles in the fluid they template the growing crystal, and they just align with the growing crystal, and so you end up with this final crystal structure. That's typically the way that crystal growth is defined. Of course, this is like a BCC crystal, so there's only one particle in the unit cell. When you have many particles in the unit cell, it's not so simple about how the particles are templating. But the point is, in a quasicrystal, they can't just template the growing nucleus, because then you get a periodic crystal. If they just fell into registry, you would get a periodic crystal. So they must do something else. So my student Aaron Keyes did this study some time ago in this Zukatov system, the point particles with this pair potential. And what he found was so the bluer the fluid, and you could start to see that there's patterns in the fluid. And these are little icosahedra, these local polytetrahedral clusters that Doi and Wales found that I showed you. They're all over the fluid. They're forming, they're breaking, they're forming and breaking. You get a little nucleus of the quasicrystal that starts to grow, and instead of growing outward and subsuming the other atoms one by one, it subsumes whole polytetrahedral clusters. It just takes them and goes, and it's just in it. So they just grow to become part of it. I think of it like the Borg. Do you guys know the Borg, Star Trek, the Borg? They just assimilate all other cultures. So this is just growing out, and the easiest thing to do is just subsume the entire locally, it's a nice locally energetically stable configuration. So it just subsumes it like that. And I mean, that's all we know right now. That's not a complete, that's not an explanation, it's an observation of that's what they do. And so there's many, many questions remaining as to how these things form. So I think that's a good place to stop. And I'll hang around if you guys have more questions. Okay, thanks.